mainly we will talk about the density of the particles in phase space. So this chapter is very much depend to your knowledge about the classical mechanics, and this is the second chapter of the Patria, and this is also, I think, the chapter 7 of the Quant. So from both of them, it's the same. And this is the gate. Actually, this chapter is the gate to ensemble theory. And using the result of this chapter, we will develop the different ensemble in the statistical mechanics. So means that microcanonical. You will let's see what does it mean, all of them. Canonical. So, and the last the grand canonical. Also this, but very softly. It doesn't came really very clearly from the Liouville theorem, but mainly the microcanonical and canonical ensemble came from there. So I told you this is a theory, so we need to prove the theory. You needed to review the Hamiltonian mechanics of classical mechanics. But I will review. I don't do the risk that about your knowledge about this topic. So I will spend maybe this lecture only to the Hamiltonian mechanics in classical dynamics. So it will take maybe one lecture just to that. And if we can finish that, so next lecture I will prove the Liouville theorem. So before that, I need to explain the main idea about the phase space. So you know, the classical mechanics, the trajectory of the particle, trajectory is defined as solution, as a unique solution to the Euler-Lagrange equation. Euler-Lagrange equation is the second order differential equation. State that if you have the Lagrangian as the function of the coordinate, so q1, q2, so qn, and the first derivative, just first derivative, because the classical mechanics want to be causal, so we don't we actually ignore safely the second derivative and the higher derivative. The second derivative and the third derivative, if appear in the Lagrangian, it means that the system is not causal. So we don't see that. I think you didn't see any Lagrangian with second derivative. Did you ever see? But there are some Lagrangian with second derivative. I mean, all the Lagrangian kinetic term is the first derivative of Q, x dot, y dot, and this thing, like that. If you have the second derivative, so it means that the system is out of the classical regime. So this is called a non-causal theory. So we don't talk about the second derivative. That's happened, for example, in the Abraham Lorentz phenomena in the electromagnetic dynamic. I think we didn't see that also. It's about the motion of the particle in the electromagnetics when the particle has the acceleration. So there is a second order term in the Lagrangian. But we are talking about the first of the Lagrangian. So Euler-Lagrange equation, we call it EL. So Euler-Lagrange equation is this set of the ordinary differential equations given like that. Here, the Qi is called the configuration coordinate. So Qi, I from 1 to n, is the configuration coordinate. Configurational coordinate. The number of the configuration, independent configurational coordinate defines for you the number of the degree of freedom of the system. I mean, if you have a 3Q and this 3Q be independent from each other, it means that the motion of the system are going in the 3 direction, like x, y, z. But not always, not always. For example, you can have the motion of the particle bend to the center, for example. This is the particle, and moving on the circle. So you know that in 3 dimension, like that. X, y, z. And this circle exists in the xy plane, for example, or any other plane. So you have one restriction here is that the distance of the particle to the center remain constant always. So this condition reduces the number of the coordinates from the 3 to 2. So the Lagrangian of this system you can define just by 2 coordinates, theta and the free force. It depends on how to define this coordinate, but anyway, you can use the spherical coordinate, for example, and use this to define the dynamic of the system. And the one of the coordinates is restricted to the condition, for example, you fix at the radius, so that's the reason that one of your configuration coordinates ignore it. And so you have it. So it's very difficult sometimes to find that how many coordinates you have to describe the dynamics of the system correctly. It's very difficult. For example, if I give you 3, ask a question. So if you have a 3 spring like that, look at that. So system like that. There are many examples like that. So Z, X, Y. So, and if you have a restriction over the spring like that, this will be the fixed, for example, fixed station, fixed end point. So you need to think that how many coordinates you have. But the main problem is to find the independent coordinate. Anyway, if you find the coordinate, independent coordinate, and this is not our task actually, you can write the Euler-Lagrange equation. So we will define a quantity called conjugate momentum. So you look at that. The Euler-Lagrange equation is the set of the n. This is the n second order ordinary differential equation. Yeah. Differential equation. So to know the system, to know the dynamical system, you needed also to know that the coordinate of the system at initial point, and you needed to know that the velocity of the system at the initial point. So, and this is the difference of quantum mechanics and classical mechanics. And this second order differential equation, we can prove and show that the solution for the second order differential equation subjected to this boundary condition, initial condition actually, is unique. But not always, if the equation is linear only. If the equation is linear, so you can have this, you can have the unique solution for your system. So conjugate momentum for any dynamical system is defined as the partial derivative of Lagrangian with respect to the Vertical velocity. This is, we call it vertical velocity because not always it implies the velocity. For example, if your coordinate is r and theta, this coordinate can be used to describe the motion of the particle in the plane, just r and the theta. So if the particle moves, so the r and theta is moving. So,
conjugate momentum is the same as generalized momentum?
Yes, it's the same, yes. It's called, but generalized momentum we use for other things. I don't know where you read it. Conjugate momentum is the momentum related to the vertical velocity. Generalized momentum normally defined for the particle in the external field. Like you have a charge and the charge is in the external magnetic field. In that case, this momentum doesn't play the role of the real momentum, for the system to write the second law of Newton, FMR. So you need the extra term, so that extra term should be added to that. And that's called generalized momentum. So this is the called conjugate momentum actually. So here look at that. In this system, for example, Q dot 1 is R dot. So R dot, you know what is the R dot is dr dt. So it's very clearly show that for you, if this is a R and this is the R plus delta R. So it gives you the radial speed. So this is the radial speed, huh? Radial speed. But the second one, look at that, Q theta dot. What does it mean? This is an angular velocity, yes. This is a delta t. But the problem is that this is not, it doesn't have the same dimension as that. This is a d length over time, and this is a d angle over time. So to make it this like exactly like that, you know that you normally needed, this is a omega in the classical omega. We needed to write omega r, huh? To make it all the same. So omega r and the r dot, they have the same dimension. So I need not always the q dot have the dimension, the correct dimension of velocity. So with this system we call it this visual velocity or measural velocity. Measural velocity. Measural velocity is the better name. Anyway, I want to pass quickly from that. So using the conjugate momentum, so the number, if you have a coordinate qi, so the number of the coordinate system is 1 to n. So corresponding to each of them, you have a one momentum, one measured moment, conjugate momentum for each one. And you can rewrite the Euler-Lagrange equation like that, dpi dt, and that this is very common to use the notation of dots. So p dot I will be partial derivative of this with respect to that. That's all. This is a representation of the Euler-Lagrange equation in terms of the conjugate moment. And look there, look at, if you're looking correctly to this equation, the equation 1 and equation 2, you see that this is the first order differential equation, actually. Because you have a first derivative of Lagrangian, and Lagrangian is the function of q dot. So finally you will have q dot. And here you will have a p dot. So it seems that the second order differential equation reduce it to 2, the number of equation doubled. Doubled.
Yeah.
Before was n equation, and here you have a 2n equation, one equation this, one equation this, but the first order. So this is the idea came to the mind that you can make another formulation of the Euler-Lagrange equation, that the equation of motion, instead of the second order, reduce it to the first order. And that was the idea of Hamilton. Hamilton was thinking about the same. So I summarize here that so the Lagrangian leads to the Euler-Lagrange equation, and this is the set of the second order ordinary differential equation. But parallel to that, you can define the pi partial derivative of this and rewrite the Euler-Lagrange equation like that, and that this is 2n number of the first order ordinary differential. So it seems that not always, it is very tricky. It's very bare idea if you think that just by passing to the P and the Q you can solve your dynamical system. I mean, not always you can solve this equation, Euler-Lagrange equation. From the mathematical point of view, if you give the initial condition, for the special case, I can prove for you that the solution for the Euler-Lagrange equation is unique. And that's all. But what is the form of the solution? I don't know. Sometimes we cannot solve this equation exactly. So we needed to use the approximation techniques. We used to use the perturbation theory. We needed to do a lot of methods. All the methods. But it's very, I told you, it's very simply thinking that if somebody think that if you pass from the Lagrangian to just to the more double number of the first order equation, you can immediately take the integral from this equation and find the solution. No, that's not possible always. But several times it helped us to have a better idea about our dynamical system. Because not always the solution is important. Sometimes the behavior of the system and the prediction is important. For me as a theoretical physicist, for example, mathematical physicist, so I call it theoretical physics better. So for me, sometimes the exact solution is not very important. I want to know that what is the qualitative form of the solution. For example, if the particle starts from here, after that, what happened for him, for this particle? Not exactly where it will go or when the motion will be vanish or when it increases. It's not the quality of that. Of course, the exact solution is very interesting. So there is a three, where I told you, there is actually three formulation of the classical mechanics, but there is a two formulation mainly used, Lagrangian and Hamiltonian. And there is a two principle, Hamiltonian dynamics. So Hamiltonian was thinking that is it possible to define a function from the Lagrangian and did this function be the first order derivative of the coordinates? So you see that the P appears here as the first order derivative of the Q and Qi appear as the first order derivative of the Qi. So you can write maybe that, and T will be explicitly remain here. We have a number of the this is the definition of Hamiltonian. If you pass the textbook, so in the Huang, there is a part about the, I didn't teach that, I don't like that. So it's about the Legendre transformation. But it's very confusing. I want to just tell you that Hamiltonian defined that as using a technical Legendre transformation. You don't need it that, not so much. In thermodynamics, we need the Legendre transformation, but here we don't need it. So this is the definition of Hamiltonian, just that. This is the definition of Hamiltonian. Okay. And the Hamiltonian equations, instead of the Euler-Lagrange equation, we have two equations called Hamiltonian equation. First order differential equations and 2n number of the equation you have. 2n number of the first order differential equation. Instead of the n second order ordinary differential equation. So this is our starting point. And just for statistical mechanics, you need to be very careful. For statistical mechanics, you have an n particle. So this n is not this. This is the number of the coordinate here. This is the number of the coordinate. I can write f. So f is the number of degree of freedom of the system. DOF, degree of freedom. I mean the number of the coordinates which you need to define your system. Okay. Okay, most of the time f is 3. You need an x, y, z, or you need a 3 coordinate because the motion more than the 3 coordinates doesn't sense to you too much. No. So f is normally 3 dimension. Anyway, 1 or 2 or 3. So in our discussions, so f is 3. And you have this particle. So for each particle, you have this 3 coordinate. For each particle, you have this system of the coordinate if you want to think it about the system of the particle. And you have how many particles? You have 2, 3, 4 and to n. So n is the number of the particle here. So for each particle you have something like that. For each particle, the Hamiltonian is sigma P dot R, PQ dot R minus L, and R is 1 to 3, the coordinate. This is the Hamiltonian for each particle, Pi. And this is the Lagrangian for each particle. So the total Hamiltonian, the total Hamiltonian will be sigma hi, I from 1 to n. So it will be sigma I from 1 to n, sigma R from 1 to 3, P dot I, P Q dot I minus sigma